Hello, everyone, and welcome again to Elektor Engineering Insights. We're at number 56 now. I'm Brian Tristam Williams, and in this episode, we're focusing on FPGAs, a cornerstone of modern digital design. Our guest today is Kevin Hubbard, an electrical engineer with more than 3 decades of experience in ASICs, FPGAs, and embedded systems. He's the founder of Black Mesa Labs and the author of the new Elektor book, Mastering FPGA Chip Design, which I'll show you there, where he distills years of hands-on experience into practical guidance for building faster, more efficient, and more reliable systems. Kevin, how are you doing today?
Good, Brian. Thanks for having me here.
Oh, my pleasure. It's more of an annoyance for you because you have to be up at 6:45 a.m., but here we are. So now Kevin's book, Mastering FPGA Chip Design, is a 333-page full-color hardcover that explains FPGA architecture, Verilog and VHDL design, and the complete EDA tool flow. It includes example projects such as UART communication, a logic analyzer, and a graphics controller, with all the source files available on GitHub, of course. So no surprise, that is our giveaway today. We're giving away 3 copies, so stay tuned for the rest of the show, and we'll give you the entry form and the code word a bit later. Before we move on with today's show, I'd like to take a moment to tell you about EE News Europe. If you're looking for the latest electronics and engineering news, check out EENewsEurope.com, which is an Elektor international media publication. EE News Europe is a fully digital publication covering the global electronics market with specializations in analog, automotive, embedded, power, smart 2.0, and wireless technologies. And of course, FPGA if you want that too. Read EENewsEurope.com and subscribe to its newsletters to stay informed about essential industry news, key events, and technological innovations. Now, Kevin, back to you. Thanks so much for joining us. I love the look of your book here. There is a preview on the Elektor website. If you scroll a bit down and you click on full screen, it's Elektor.com. This is a good moment to answer one of the questions I saw from Mur wants to know, I require the printed book. How do I obtain it, please? Advise me, from UK. Well, it's Elektor.com. That's our store. Just put FPGA in the search bar, and that's the easiest way to get there. And yes, we ship worldwide. So there's Kevin's book. And as I said, here's a preview. Kevin, I'm looking at this book and it looks great. I don't have a copy of it yet in print, but it starts off with the very
I do, and it's a handful.
It is, and you're very proud of it, and I would
Yes,
be
I am.
too. So it starts off with basic digital logic design, and it kind of reminded me of this book I really enjoyed studying from about 25 years ago, Digital Fundamentals. 25 years ago was the year 2000 approximately. But I didn't realize at the time that this book was already about 10 years old. So we're talking 1990. Takes them 641 pages to get into programmable logic, and then they don't mention FPGAs at all because I think those are still new on the market. But they talk about PALs and FPLDs and so on. So what prompted you to jump right in to digital logic design and starting off with CMOS, of course? I mean, I'm used to TTL, but you went straight in because that's an older technology now. What made you want to write this book?
Well, I've always been fascinated with digital electronics. I got started in the 1970s as a kid with TTL logic, like you as well, and moved into the CMOS in the 1980s, and then pursued my degree as an electrical engineer. And at the time, one of my first jobs, I was doing a lot of embedded microcontroller work. And I had the opportunity to do some PAL and some CPLD designs, and like you said, just really small stuff like Altera 7064 with just 64 flip flops and 64 LUTs. It was a great starting point in the early 90s, and it stuck. And I moved away from doing software engineering to just doing strictly digital design. And the FPGA technology really took off in the 1990s and 2000s. And, we've gone from just a few hundred flip-flops to hundreds of thousands of flip-flops and LUTs and chips now. And it's just an amazing time to be doing programmable logic design. As I've been doing this for the last 30 years, I've accumulated this knowledge base that, I just want to share. And there's so many details, and it's so easy to get into FPGA design and to basically do it wrong, to write Verilog that compiles and simulates, but you end up with a slow design, or a design that consumes too much power, um, or a design that's just too large, and you end up spending too much money on an FPGA. So I've learned a lot of tips over the years for making small designs and fast designs and low power designs, and I just wanted to share that with the world.
That's great. Thank you for sharing. I mean, when I see the word FPGA, I'm intimidated. I am currently going through this course, Learn FPGA Programming with Verilog. It's also from Elektor Academy Pro, which you published your book under, and it comes with a red pitaya. So making a little bit of progress.
Great.
But when I say I'm intimidated, and then I open the first page of your book and it's flip-flops, I can work with that and hopefully follow along as we go along. But looking at the comments section, a lot of interesting stuff here. We start with, sorry, not the comments, the contents. Structured Verilog, VHDL. Where it really gets interesting for me is, example design, video graphics controller, CRTs, VGAs, and then you even have some test patterns and frame buffers and text buffers. And ASCII art, it's amazing what people are doing nowadays. I mean, I'm a retro computer guy, and people are using FPGAs to just replace the video chip outright and get VGA output from that. Was that a lot of fun working with?
It is, and that's where doing digital logic design is a lot of fun, is when you can have the opportunity to generate live video, because it's something that you can't do with like an Arduino, or it's not very easily anyways. With FPGAs, with everything running in parallel, it's easy to pump out pixels and draw live video, and you get instant response of typing your design, loading the FPGA, and it's like, oh, well, there's my colors and there's my lines moving around, and it's a great application for FPGAs.
Yeah, and first time I saw programmable logic was in a cartridge for my Texas Instruments computer. TI themselves made TI Extended Basic, and those were naturally ROMs that they made in factory, but a smaller third-party operator made a Super Extended Basic, and they used programmable logic. And I misremembered thinking it was about 87, 88, and I thought it was an FPGA, but I went and had a look at it today, and it was a PAL. So what's the difference between those early PALs and things like field programmable gate arrays?
So the early PALs, sometimes they were burn once, so you had one opportunity to burn your design into the PAL, and then if you had to change the design, you needed to get the new chip, so it's kind of expensive. They evolved to flash based, and that kind of turns into CPLDs, where you still burn the chips, but you could also erase them, just like you do with like a USB flash drive. Most FPGA and some FPGAs, Actel had some anti-fuse technology. I don't think that was one-time burn, and then I think they also have some flash-based. But the majority of the FPGA market is SRAM based, and so they have a SRAM configuration where on power up, you have to load what's called a bit stream, which is just ones and zeros that says, okay, connect these what's called programmable interconnect points, which is, if you can imagine, imagine like a road system where you have one road going this way and one road going that way, and you have a drawbridge that can connect the two. That's called a programmable interconnect point, and each one of those is a binary bit that is part of your bit stream. And as the designer, you generate this bit stream going from Verilog or VHDL, and you compile it into a with synthesis into a net list, and then like Vivado tools will generate the bit stream from it. That bit stream then goes into a flash prom, and on power up, the FPGA has just enough brains built into the FPGA itself to issue a command to this flash prom that says, okay, dump the contents, give me a bit stream, and then that bit stream does a raster through the FPGA, either opening or closing all those programmable interconnect points that connect all of the it's called the LUTs, the lookup tables, and the flip-flops together to make a working design. And then if you want to change the design, you just erase that prom, which is like an external dollar prom, flash prom, and then you can put in a new design in the FPGA.
Great. And I remember learning those different, you talk about field programmable. There was ROM, then there was PROM, then there was EPROM. And yes, I have had experience erasing them with an ultraviolet light, as I'm sure you have. Then EEPROM, then
Yes.
Flash. So the early days of FPGA adoption, what was it like designing before these became quite mainstream? Were they expensive?
They were, and trying to get into it as a hobbyist was difficult. I remember asking an FPGA, my FAE, if I could get an eval FPGA, and it was, I want to say it was like a 4036 XL from Xilinx in the mid 90s, and it was like a $500 part, and
Wow.
the tools themselves were also, they didn't have any free versions back then, and so just the basic version of the tool was, in the 90s was another $500 or something. So I kind of begged my Xilinx contacts is, hey, I want to get into this more. Can you help me out? And they obliged. Well, that was great, because then I could both do my day job using company tools and then go home and do my own thing and learn in other directions. That was very beneficial for me. And yeah, the early tools, they're also slow. And it was, even for small FPGAs with, just 1,000 flip-flops and stuff, it could take 10 hours to route the design and make timing. And so you can get in this spot where if you have a really tough design, you would work on it all day in the office and then press go and then go home and come in the next morning and hope that it finished.
Yeah. Well, I mean, I was jealous of people those days who had companies with deep pockets to lend them the toys, which I didn't. I had to tinker and make my way, but I guess I may have learned more stuff by making do with what I had. Let's take a moment to greet our audience. We've got people from all over the world. Patrick says bonjour from France. We've got another bonjour. We got Frank. He's a regular from Valen, Belgium, Barcelona, the UK, Poland,
All over. Wow.
UK, Germany, and so on. I won't mention all the countries in the world. There's our friend Sebastian from Baltic Lab. He'll be joining us tomorrow to have a chat on our Elektor Lab Talk show. And we've got the Eastern Hemisphere from India. Just get these greetings out the way, and then we can get to an actual comment from TF Mulder, who says, you can have a masked version of your finished FPGA design. I suppose that's for the bigger boys, right?
Yes, and it's, the industry has gone back and forth on this. Altera in what year was it? 2010-ish. They were going big on what was called a hard copy, which was a masked version equivalent of their FPGAs, and so the FPGAs were a little bit smaller. Or the ASIC version of it was a little bit smaller than the FPGAs, and so you could get the cost down. So, a $100 FPGA, you could get an ASIC version of it for, maybe $40-50. And how it worked is they would build what's called base wafers. And I wish I had a wafer with me. I don't, unfortunately. But they would build a base wafer of their FPGA, but in the ASIC flow, and they wouldn't have all of those programmable interconnect points. They would be gone, and they would still have routing on some of the bottom metal layers, and eASIC was another big vendor of this. They would reserve the very top metal layer for the user programmability. And so all those pips that used to be SRAM programmed with that big scan chain going through, as a designer, you could go to the vendor and say, well, okay, I want to do a hard copy or an eASIC version of my FPGA design. And you would then only have to pay for a single reticle. And since this base wafer, the vendor is already making for multiple customers, the NRE comes way down. And it's a good flow, but you're always, you're always behind the industry, because the FPGA vendors are always, they're turning the crank with the Moore's law, and getting the latest generations out as soon as possible. And meanwhile, if you're doing your prototyping, and I'll take an example. Say you're prototyping the 28 nanometer FPGA, and you want to do a hard copy of it, and by the time you get there, and by the time you get your reticles built and stuff, the FPGA vendors, they've already built 14 nanometer FPGAs, and so
they won't
the
roll
cost
back
goes
for
down.
you.
I'm sorry, what's that, Brian?
They won't roll back to older technology for you.
No, they will, but the newer technology is going to be faster, and it's going to be smaller, and so your cost savings are less.
Yeah.
Yeah.
So it's speed, area, power, and reliability, which I think are the 4 important ones for you.
Yes.
Anything else that you factor around when designing?
Well, definitely cost, and I guess that comes into the area. Yeah, it's keeping the cost down, and also, FPGA vendors, they bend their parts for different speed grades, and so if you do a design and you're not cognizant of designing for speed, you might have to bump up to their highest speed grade, and basically that's like the top few percentage of when they fab the raw die of the FPGAs. They test them for performance, and they will put the cream of the crop in a specific bin, and they can charge more. So like 20-40% more for those faster parts. And so if you design for speed up front, and you can say, well, I always want the slowest speed grade that they have, you can save a lot of money that way.
Cool. And there could have been 100 different projects you could have done in this book. You had to choose. I mean, you got the UART, which, funny story, I was learning how to program on an 8051 Intel, and I needed a UART, so I bit banged one instead of bothering to learn how the built-in UART already works, because I was studying at the time. Again, it taught me serial protocol, so no regrets there, but it's actually quite simple to use. But you've got a UART in the book, a logic analyzer, graphics controller. How'd you choose those, and what could you have also included?
So I chose those 3, well, 2 of the 3, the UART and the logic analyzer, because they were open source projects that I had been working on for years, and they're also on my my GitHub site. The VGA controller, that's just something that I just enjoyed doing. I've enjoyed generating graphics with FPGAs forever. And it's you were talking about TI computer earlier. I remember in the 1980s, I had an Apple II computer that Steve Wozniak designed, and it was a very simple computer with there weren't any custom computer chips in it. It had a 6502 8-bit CPU, and basically a bunch of TTL chips. There was no graphic controller or anything like that. A friend of mine in middle school, he had the TI 99-4A, I think is the name of their 8-bit computer.
Yeah, that's what I've got behind me.
Yeah, one right. Okay. So the TI had a sprite controller, which a sprite controller is it's not really a GPU, but it's a graphic controller where you can in RAM, you can say, okay, I want to draw this image. So say if you want to draw an image of a hand, you draw the pixels of your hand, and it might be, I don't know, 16 by 16 pixels or something. And that sits in a RAM spot, and that's called a sprite. And that sprite, you tell it the X and Y location of where you want to put it on the screen, and the hardware takes care of it for you. So the software can upfront program the bits of the hand, and then while your program is running, all it has to do is increment like the X and the Y, and your hand moves all over the place. I was amazed because with just basic programming, which was very slow back then, on an Apple II, I couldn't do anything like that. And my friend showed me this. He drew like a stick figure in BASIC and had it zip across the screen like Mario on an NES Nintendo. Yeah. And I was amazed. And so that was something that's like, well, how do those work? And so for this book is like, I'm gonna build a sprite controller, because I was always amazed by my friend's TI computer. And so that was one of the examples for my VGA controller, was doing a sprite controller, and it works.
That's awesome. I'd like to check that out.
Yeah. And as far as the UART, so one of my frustrations with the electronics industry is it has gotten so complicated for just people to just dive in, and things that I took for granted back in the 1970s and the 1980s. My first computer was a Tandy TRS-80 Model 1, and it didn't have slots. It had an expansion port on the back, and it was the raw CPU bus of the Z80 processor, which brought out 5-volt TTL signals. And nobody told me that I couldn't put my own stuff on that, right? So Radio Shack, they sold disk drive interfaces and modems and all these other things that they wanted to sell, $500 peripherals to expand your computer. But meanwhile, I was like a 9-year-old kid. It's like, well, what if I do something with that port? And so I built stuff with 74374 latches, and on breadboards, and everything back then was 1 megahertz, so you could actually do stuff with breadboards. And I just started putting logic gates on the Z80 bus and driving LEDs, and it's like, well, this is really cool. And it's like this bridged my passion for digital electronics with this new thing I was getting to, which was computers. Everyone was getting into computers in the 70s and the 80s. Over time, that was taken away from all of us, that ability to hop on to the CPU bus and drive LEDs. The very last thing that you could get access to was the serial port and the printer port. And the printer port was nice because you could bit bang stuff. And so I did some designs for industry where I used the printer port on an IBM PC for controlling test fixtures and stuff like that. Well, eventually that got locked down when we went from MS-DOS, which everyone was basically root. If you're familiar with Unix, with root,
Yep.
you have access to everything.
Even on the first Windows 95.
Yes, even on Windows 90, yeah, you could still access everything.
Debug.
Right. Well, then Windows NT came along, and Windows NT was a great operating system, but it protected things from the general user. And like one of those things was the printer port. And so now you could no longer bit bang the printer port. You could only use the printer port if you wanted to, print something from Microsoft Word to your printer. And so out of desperation, it's like, well, now what am I going to do, right? And for a while there, I pivoted to doing all my hardware development on a Linux box where I could log in as root and still access the printer port. But then, the writing was on the wall. It's like, well, the printer port's going away. What's left? And this was, I don't know, early 2000s. A company in Ireland, I think, called FTDI. They came out with some custom
FTDI 232.
Yeah, FTDI 232. It had a USB interface on one side and essentially an RS-232 interface. It was TTL levels. RS-232 was like plus or minus 15 volts or something. But the other side was TTL 3-volt logic that could give you a UART bit stream at up to a megabit. And with that, as a user, you could just open up a COM port, even within protected windows, and say, oh, I want to talk to this serial port. And so from that, you can talk to hardware. But on the FPGA side of things, you need a UART. And so early on, I designed my own UART for transmit and receive. And that's how I talked to, I don't have my FPGA here handy, but we were talking about bitstream configuration. So one of my early FPGA boards that I designed was a Spartan 3 FPGA, 90 nanometer Spartan 3 FPGA from Xilinx, and it had a Cool Runner 3064XL. No, that's not the right part number. Anyways, it had a CPLD in it, and that CPLD I implemented my UART in. And with that UART, it would convert an RS-232 serial bit stream into an FPGA configuration bit stream, which means I could blast in my FPGA designs just over a USB port using the FTDI chip. and I wouldn't have to use JTAG and program a PROM all the time. I could do that live. And then that evolved over time. It's like, well, I actually want to talk, read and write. I say registers, and I don't mean flip-flops. I mean like a software controlled register. If like if you had an ISA video card or something, there'd be registers that the software programs things like the sprite XY location, that sort of stuff. I decided, well, I can use USB via FTDI to interact with FPGAs for writing and reading internal software registers that on a full up design you would use like PCI Express, but as a hobbyist, FTDI with UART is the way to go. And so I developed this protocol I call Mesa Bus Protocol that is just that, and allows you to take a single FTDI UART stream, connect it to daisy chain multiple FPGAs, and then interact with those FPGAs from software. And then I wrote a bunch of tools like BD Shell, which is pays homage to Steve Wozniak's monitor in the early Apple II, where you could access anything inside Apple memory. If you did a call -151, it brought up this interactive console that you could read and write anywhere in Apple II space. And I was like, well, in FPGAs, I want something like that. So I wrote something called BD Shell, and it allows you to read and write 32-bit software registers anywhere in FPGA space. And then I built upon that. I built my my SUMP logic analyzer, which is it's a logic analyzer like Xilinx and Altera have their ILAs that exist inside FPGAs and allows you to see what's going on inside and debug inside your FPGA. I did a different spin on that, which was my version, which actually began from someone else's original project called SUMP. My version uses run length encoding compression, which means I need a lot less RAM. And so a vendor ILA, you might throw dozens of SRAM blocks to capture a few thousand samples of a handful of signals. My SUMP logic analyzer is designed so all you need is one RAM block. With one RAM block and using real-time RLE compression, you can get useful information out. And again, that comes back to keeping your FPGA design small and inexpensive.
That's great. I mean, I wish I knew more about FPGAs, especially at the time. For example, I took an entire video section out of a TI-9948. It's the video controller and all of 8 RAM chips, and put them on a breadboard, which worked. So nice. I could run it from an Arduino. But if I knew more about FPGA like you did, I could probably replicate the whole thing without having to rip it all apart. But you remind me of good times. It was go into the command prompt or the DOS prompt, even if it was Windows 95, and you just type debug. And if you wanted to turn on all 8 bits of the parallel port, it was called a parallel port because it was used for printers, but basically it was a GPIO, I think, running on TTL logic. And if you wanted to make all 8 bits of the data ports ones, you could just go 0378FF. So it's out to port 378, all ones. And speaking of TTL, TF Mulder also says the TDL 7400 series you can still use in Altera Quarus. Nice to play with. And I know we didn't come here for retro computers, but there's a lot of interesting video, apparently. Frank DeHart says Atari ST's Blitzer. Yes, the Atari and the Amiga had Blitzer, and they were both 68,000 Motorola based, but they came out much later than the TI-9948 and the Apple IIe. Funnily enough, my father had an Apple IIe in the same room as I had the TI, and I was plugged into the TV getting 16 colors, and I wanted him to use the composite output of his Apple IIe so I could play Choplifter in color. And he said, no, the Apple's not a toy. So he was using his flight simulator on a green screen.
Choplifter was amazing. That was the game that I still play on my retro Apple II. It's like, well, it made the Apple II look like it was a real machine. And it was I can't remember the author's name now, but he
wrote a bunch.
Yes, He wrote the whole thing in assembly language, which was necessary back in the days, because there were no C compilers for the Apple II. So if you wanted something to run fast, you wrote it in 6502 assembly language.
Yeah, absolutely. I remember program files being printed in Compute Magazine in machine language.
Yep.
And you had to type out the zeros, all the hexadecimal. And if you got one thing wrong, you have to parse that whole.
Start all over again, yeah.
Christoph says, when designing a graphics controller on an FPGA, what affects its performance and how can tools help test and improve it?
What affects its performance and how can tools help test and improve it? I guess if the question's about timing performance, like the pixel clock,
or how much power can you get from it? You're not going to get NVIDIA GPU level performance, but there must be some sort of thumb sucks you can use. Rules of thumb, sorry.
Rules of thumb. Yeah, so when I do video, I try to stay below 100, what's called the dot clock, which is the pixel clock rate. I try to stay below 100 megahertz. Then it makes time enclosure on the FPGA designs easier, and that limits you to a resolution of like 1280 by 1024, I think. And I'll do a lot of designs that are like 800 by 600 is a sweet spot for doing VGA graphics, because then you can have a 40 megahertz pixel clock. And if you're doing design with 40 megahertz, meeting time enclosure with FPGA is really easy. And so for anyone wanting to jump into doing a live VGA graphics, my example design is a perfect starting point because it uses a slow pixel clock.
Awesome. So slow pixel clock all the way.
Yeah.
Let's go back to our giveaway, since we're about halfway through the show. As promised, here's our giveaway. It's a copy of Kevin's book, Mastering FPGA Chip Design. And the URL is elektormagazine.com/Elektor-engineering insights giveaway. And the code word is FPGA 2025. I think that's quite appropriate for this. So we're giving away 3 copies of that. I won't enter, so I'll give you guys more of a chance to win. And good luck with that to our audience. Let's go back to some questions and comments here. This is a comment from Jürgen. Started out with an SCMP2, I think they call it a SCAMP or something, and replaced the TTY machine with it. All these learning opportunities are gone. My students can only do Arduino stuff if they find libraries for sensors, etc. If not, they can't do because they never learned or experienced real basics.
Basics, yes.
I feel you that on.
Yeah.
Yeah, I was a bit taken aback when Arduino came out, because I was like, I learned so many years how to do this stuff myself, and now you just plug and play. But then I realized later, yeah, it is important to know the basics. And I've been on forums where you think people have an actual interest in the topic, and they're just coming on there to ask you to do their homework the night before. But at least Jürgen's having fun now on an SCMP2 realized in FPGA.
Great. Yeah, Arduinos are great when they came out because they made microcontrollers so much more accessible.
Yeah, Raspberry Pi as well. Clement says, it's the basics that give projects their creativity. Now that we use an Arduino and it works relatively well, but it's so interesting to know how a microprocessor is wired. Yeah, I don't know how a microprocessor is wired. I never got that in depth, but I could program that TI with toggle switches, 1s and 0s to compile from assembly code.
So this is a great great segue to a new project I'm working on, which is system on chip design with the RISC-V microprocessor. I hope to turn it into a book. I'm in the investigation stage right now, but I've I've designed my own RISC-V CPU. I call it the Femto CPU. It doesn't do all 47 RISC instructions, but it does 5 RISC-V instructions, which is enough to do the Blinky program, and blink an LED and FPGA from C. And I'm doing this as a learning project for people who want to know how microprocessors work. You mentioned that the 68,000, that was where I got my start with assembly language. Right? I did a lot of 68,000 designs in the early 1990s. And I pivoted away from that to FPGAs for the next 30 years. But now I have this opportunity of going back, and it's like, well, RISC-V is this open source 32-bit and 64-bit ARM CPU equivalent out of UC Berkeley that anyone can just download, Verilog source files for it and put it in an FPGA. And so I'm working on this project where I'm building up. I have my own RISC-V, like I said, it has only 5 instructions to just learn the basics of assembly language programming and how the instructions get out of RAM, go into the pipeline, and load registers, increment values, count in a loop, flash an LED, and rinse, repeat. And then I'm moving up to, well, this is how you bring in a full 47 instruction RISC design and do a system on chip, which is the CPU and peripherals like UARTs and VGA graphics and all sorts of other things, SPI and I2C. So I'm trying to put together multiple chapters and have it be a learning thing of starting with very basics of assembly language on a RISC-V CPU and working up to I'm using the Hazard 3 RISC-V core from Luke Wren from the Raspberry Pi Foundation. That is actually in the chip is the 2350, I believe, the Raspberry Pico. Yeah. It's that ASIC, which Luke is a ASIC designer at Raspberry Pi Foundation. That chip has both an ARM processor in it, and then right next to it, it has his RISC-V Hazard 3 implementation. And so I'm doing a lot of work on showing how you put that soft CPU inside an FPGA and how you debug it with JTAG tools and like Sager JLink and OpenOCD and GDB and things like that.
Yeah, Luke's done a bunch of interesting stuff over at Raspberry Pi. I'm just looking at his page there, and yet there's RISC-V on the Raspberry Pi Pico 2. So it's interesting that the overlap there between your FPGA work and RISC-V that you're working on.
And Luke's been helpful for me on this project. I just started it a month ago, and so I'm very new to RISC-V, but I have a lot of 68,000 experience, and so there's a lot of overlap, and a lot of things haven't changed in the 30 years. Like I was using GDB, the new debugger back in the 90s, and while that's still around, and there's still ELF files, ELOAD, and things like that. But I was very impressed with his core, and I already know that it's been in an ASIC, and so I have faith in it. And so far, everything just works. Like the debugger is a little bit tricky to implement in a chip design, and it just works. And so I'm very happy with this project.
Awesome. As a comment from Jürgen, one good processor to start with is the CDP 1802 as a chip or as VHDL. Do you know it?
I do not.
Cool. And another comment from Frank Eitrish, I think. Yeah. For very small designs and experiments with analog parts, Renesas has chips named GreenPack SLG4XXX. There are only a dozen programmable digital blocks, but also analog programmable mixed signal matrix and an EEPROM. In mass production, there will be versions with mask connections instead of programming. So you're nodding?
Yeah, I've heard of GreenPack. I haven't done anything with them, but yes, it's cool technology, programmable analog.
Yeah. I mean, programmable analog FPGAs are often, they look like Lego for engineers. I wish they were as easy to play with as Lego, but I'll get there. What's the best mindset for someone new to them? Like hardware first, software first, or somewhere in between?
Gosh, I think Arduino is a great starting point. and our Arduino, and maybe just hooking up an Arduino to a breadboard with some simple digital chips, which unfortunately, when I got started in electronics in the 1970s, and here in the States, we had Radio Shack stores, and they had an aisle of electronics where you could buy 7400 TTL, and then eventually and 4000 CMOS chips. And that was like my entire world. And as a little kid, you could just go and spend 99 cents and you could get a flip flop.
Yeah.
Yeah, you can't do that anymore. um, but there are places where you can't get. I mean, Elektor is a great example. The Elektor sells kits and things like that, that you can go to, and you can get starter kits that have things. And I would say, yeah, if you want to get started with digital electronics, is learn the basics of C coding with Arduino, and then figure out how to make digital chips do stuff, because you can use the Arduino to provide stimulus to chips. Otherwise, you're stuck with push button switches and things like that, which can be misleading, because push button switches bounce.
Yeah.
So yeah.
Exactly. Well, this book that I told you I loved learning from back in the late 90s, they start off with basic and or and not gates, and they build up from there, and then you work up to parallel adders and parallel look ahead, carry adders, and just blew my mind that you could, all this computing hardware and power that we have here, it's just all the same thing. It's and or and not at large scale, and we're at artificial intelligence now using just those gates. So
yes.
FPGA, I think, is a good place to tip your toes in.
Definitely. And there's a lot of great, so in my book I use the Vigilant Basis 3 starter board, which is fantastic because it has lots of LEDs and lots of switches.
Sorry, I'm trying to zoom that in.
There we go. Yeah. My absolute favorite thing about this board is that Vigilant included a PIC microcontroller on it that connects to a host USB port. And what it allows for you to drop the bit file, which has your FPGA configuration bit stream, just onto a flash drive. And so you can take a regular USB flash drive with a bit file that's straight out of Avado and plug it into this board. And when you power the board up, the FPGA will configure from it. That saves a lot of time and a lot of hassle, because normally with an FPGA, you need to use a JTAG programmer, and you have to use the what was used to be the impact tool, which it works, but it's a slow process. And with this board, with that helper microcontroller, it just streamlines the whole process of configuring the FPGA. This is a great starter board. It's like $150. And yeah, awesome. all the example designs on my GitHub target it, but you don't have to have that board. You can retarget all my Verilog and VHDL designs to pretty much any vendor FPGA board. That I think the VGA connector is the most complicated thing that I use on that board.
I've got a question from Jürgen. He wants to know when we'll go from general talk to more talk about the book. So I'll put the book up if that makes you happy, Jürgen. But in terms of teaching beginners, I don't know how much time you spend with beginners, Kevin. What do you find they most often stumble over? Is it HDL? What would it be?
I find that the biggest stumbling block is not understanding the fabric of the FPGAs. So I started the book with the beginning CMOS transistor theory, because that's important to understand that, all these gates inside the FPGA, they're actually transistors, and all these transistors actually have a gate, not a gates, but a transistor gate. And that gate is capacitance, and so you have to be mindful of how many transistors you use, because you keep on adding capacitance. And like this picture of the D flip-flop, that tells you that a D flip-flop doesn't actually have just one clock input to it. It has 8 clock loads of 8 CMOS gates. And so every flip-flop you use in a design is adding more capacitance, which is slowing down your design. And so an easy thing for a beginner to do is to just throw too many resources on a net and that capacitance is just slowing that net down. Another thing is just for learners is to understand how the FPGAs interconnect, the whole thing with the pips and the routing. And if we go forward a couple more pages, I draw some simple, this picture on the right. It shows an example of, the very simplest ASIC I can think of, which is 4 flip-flops compared to an FPGA equivalent. And that picture shows how you have all this metal routing resources that are, diffused in the FPGA, and you only get to use some of them. And when you use too many of them, well, then you can no longer get your signal from point A to point B, or if you do, it takes a long, long way. I think the easiest way to understand the difficulties of FPGA design is to imagine like a road system. Like if you're in the United States and you want to drive from Seattle to Manhattan, well, but you have a whole bunch of cars, you want to make the trip, but only one car can use one lane, and you can't put cars back to back. So on a road system, it's like, well, you'll put as many cars as you can on the freeway on I-90, which pretty much goes across the country. But once you have one of your cars in each of those lanes, where do your other cars go? And with FPGAs, those other cars go on the side streets. And they go in between all the little towns, and they will get from Seattle to Manhattan, but it might take 3 weeks versus however long it is, 5 days for the same trip on the freeway. FPGA routing is exactly like that, where you have limited routing resources, and if you try to make a 128-bit wide bus or something, well, you're going to end up with problems. And so one of the things I really try to preach in my book is use narrow lanes whenever possible. And in fact, my sump logic analyzer, it uses a 2-wire interface, kind of like I squared, well, actually more like SPI, where there's a single serial signal going one way and a serial signal going the other way for each of my compression pods, which means that if you have your production design is already 90% utilized of your FPGAs, if you wanted to add my sump logic analyzer to it, well, I'm only going to require 2 wires to add a sump RLE pod to test your logic over here and talk to the controller to go into USB over there. And so if you can implement designs that use just a few wires to serialize data communications, that's going to make the overall design a lot faster and a lot smaller.
Yeah, and I think one of the paradigm shifts that's been a bit unsettling for me is how in the past, if you wanted to do something like make a pulse train or toggle a flip-flop, you could use just passive components or a transistor. And now it's often cheaper to just waste most of a tiny microcontroller, which can do the same job for you, and yet it seems like such overkill. That's a segue to Eric's question here. Whenever you have a DIY project in mind, what are, in your opinion, the main criteria to decide whether you should go with standard MCU programming or FPGA? He admits, like I do, it looks very intimidating.
Yeah, I get that. And for most, honestly, most DIY projects, microcontrollers are probably the best solution. FPGAs is more about doing massively parallel computations, things at real-time speed, not at microsecond or milliseconds that microcontrollers might be dealing with, but within nanoseconds. So things like live video graphics generations on when you don't have access to like a GPU. VGAs or FPGAs are great for that. What other applications are good for FPGA? There's been some really cool projects that I've seen, like retro computing projects that have used the Raspberry Pi Picos for, like, there's one that converts it sits on the Apple II 8-bit bus, and the Pico microcontroller looks for writes to the video address space of the Apple II, and then the Pico bit bangs out HDMI graphics on the other side, so you don't have to use composite graphics for the Apple II now. You could use this Pico project for doing it. And I saw that, I was like, wow, that's really cool. As a retro enthusiast, that's great that you can get digital graphics out of an Apple II. But a microcontroller is not the right solution for that. Really, if you want to put something on a computer bus, you want an FPGA. And in this case, the computer bus was 1 megahertz, so the Pico was plenty powerful for doing that. But for real applications, even for embedded microcontrollers that might have 50 megahertz buses or something, you want digital logic that can interact in real time.
Yeah, that's a weakness of mine. I go for the microcontroller option because I don't know how to do FPGA, but oftentimes it's wasteful or limited resources. Question: to reduce FPGA power consumption, there are methods for gating the clocks to minimize the number of switching flip-flops. Is there a chapter in the book for this?
Absolutely. It is the Design for Power, chapter 24.
Great, we memorized it.
I wrote it down.
Here we go, Design for Power.
So there's, let's see, 24.5 is global clock gating. So a global clock is a clock that spans the entire chip. What's called a buff G is the clock tree buffer. There's always an input to that that's enable. And so if you have a clock that's always alive, you can use that clock that's always alive to turn off some global clock buffer and just save a ton of power on FPGAs, because CMOS power, once you stop clocking it, it essentially goes to zero, ignoring leakage. The other useful thing is regional clock gating, which that's kind of fuzzy, but 24.4, page 240, you can actually implement region. In fact, Brian, can you bring up that page 240? There might be an example.
We don't have the whole book here. This is
I'm sorry. Okay, my bad. Basically, within a process, if you have, let's say you have a 32-bit counter or something, within a Verilog process, at the very top of the process, you can just have an if statement that says, if count enable equals 1, then count, and then that's it. Well, the Vivado tools from AMD Xilinx, they're smart enough to say, oh, well, that can be a regional clock buffer, that enable signal. And so rather than feeding that enable into the LUTs that eventually end up going into a counter that go into the flip-flops, that enable signal will actually go into a clock buffer that's just for the CLBs, so just for that small group of flip-flops. And if you do that all over your design, you'll be saving power whenever the small portions of your design aren't necessary. Like if you don't need to be counting for something.
Jürgen says people might want to have a look at some examples he went through based on the NAND land information. He has a small group on Facebook, FPGA Go Board NAND land. Looks like some interesting stuff there. Don't mind if I join the group, Jürgen.
That's fun.
And then speaking of social media, how do you platform for example, to promote your book? How many platforms are you on?
Mostly Twitter or X.
Okay.
X now. LinkedIn, I mention it now and again. And that's pretty much it. And then all of my development. So my my book was started out as a blog series on my Black Mesa Labs WordPress site, and a number of people convinced me to turn it into a self-published book. I was going to self-publish through Amazon, and that's when Elektor contacted me and offered me a book deal. So now it's published through Elektor. I'm repeating the process with my new book idea, which is the RISC-V idea system on chip. And it's beginning as a blog series, and I'm trying to write a new chapter basically every weekend, add a new chapter to it. Brian, if you click on the first paragraph.
Cool.
It'll show you the Yeah, so there's an example of a RISC-V SoC, and it's got the table of contents of what I have so far. And so I kind of want to start out
Wow.
with, what system, what SoCs are, and then give a brief history of modern computer architecture, and then work into RISC-V, and then I introduce my femto CPU design, and then work up to the Hazard 3 design, and give a bunch of example designs with peripherals like the VJ graphics controller. And so I'll flush this out as an open source blog series, and then I'll start writing it as a manuscript, and then certainly if Elektor is interested, I will try and publish another book with Elektor and turn it into a polished book.
I'm sure we will do. And kudos for your dedication to working every week to get these chapters out.
Thank you. It's
There's a
passion.
question: how do you approach prototyping? Would you prototype in C first or HDL?
Oh, HDL. Definitely. I write in Verilog and simulate, and I don't go straight to FPGA ever. The model sim is by far my favorite simulator for simulating Verilog, and you can get model sim licenses from Intel/Altera for small home use sort of projects. I just write Verilog and simulate it, and get good feedback that it's going to work in hardware, and then push that synthesis button and do the place and route, and yeah, that's my flow.
Cool. TF Mulder's got a question for me. If Elektor can make an FPGA board that is low cost for the Elektor makers, I think that's a great idea. I will take that up with the powers that be.
So I'll do a little plug. So one of my Black Mesa Labs projects was an open source FPGA board, and Trends Electronics in Germany. It's not going to be in focus, is it? It's a little Spartan 7 board, and it's available for like $40. And it's you can't see it, but it's either a 100 mil pitch that you can plug into a DIP breadboard and get 32 IO out of it, or there's a 50 mil pitch castellated vias on it. So if you wanted to solder it to your own bigger project, you could get 64 IO, all 3-volt. And then it has a JTAG connector and an FTDI connector on it, and a DRAM chip. It's a low cost board. It's $40.
Nice, not too
And
bad.
it's built for building up a bigger project. Unlike most dev boards, like the Basis 3 board, they're all filled out and all their connections. Most except for the PMOD connectors on the sides, all the IO on the FPGAs are going to the switches and the LEDs and stuff like that.
Awesome. I think we have time for one more question, but we've got a whole bunch of comments, so I think there's some value in here at all these comments that are coming in. So I would advise our audience to take a look at the comment section. There's plenty going on here. It's a very interesting topic. There was a question here for you, Kevin, and I think I'll make this the last one because it's nearly 7 a.m. where you are, and you've got to get your day going. But here's a question from Ziad. What is your opinion of the Nexus A7 board? Do you recommend?
I would have to look that up. It sounds like that's a Digilant board.
That's what comes up for me. Digilant, yeah.
Oh yes. Access video. Oh, actually, yeah, I have that board. That's a great board. And it's very similar to the Basis 3. It's more powerful. It costs more. It has the same boot infrastructure. Where you can boot off of the USB flash drive. It also has a small OLED display. It has the high density connector on the right there for if you're doing your own PCB. It's more high end. So if you were like a KiCad user or something and you wanted to do a high density interface to an FPGA board, that's a great starting point. This is more of a professional board than the Basis 3 is more of a, I would say, entry level board. But yeah, that's a good board.
It looks like it's about $600 US, but to answer your questions, yeah, yes, Kevin.
Yeah, somebody talked about the Lattice iStick. Yeah, I bought a Lattice iStick years back, and it was $20 back then, and my very first SUMP2 was implemented that, and it's a really small FPGA. I want to say it's 1,000 flip-flops or something. And so that was a real challenge, because I had this working logic analyzer that did RLE compression, and I had to really optimize it to fit in that $20 lattice iStick, because I knew that it was a popular development board.
Well, that's great. Well, there's your answer. And that's the final answer for today, as we have to let Kevin go. And Kevin, thank you so much for spending this hour with us. It was very interesting, and we had a lot of engagement in the comments.
Thank you, Brian.
And thank you to the audience for joining us from around the world. I didn't see anyone in South Africa today, probably because it's a public holiday here and I forgot about it. So here I am. Enjoy the rest of your day, Kevin. And for the audience out there, have a great morning, evening, afternoon, wherever you are. Thank you, and goodbye.